Oh, hey, didn't see you there. My name is Logan and welcome back to the lecture hall. For today's Math 2B series, we are covering section 6.2, and that is calculating volumes of curves. Now, what the hell do we even mean by volumes of curves? Curves are lines. Well, what if we wanted to find the volume of this curve rotated about this, rotated around the x-axis? Well, this would create like some sort of vase shape, and how would we do that? Well, if we let S be a solid that lies between x equals a and b, that would be our red line. And if the cross-sectional area of S is in the plane px through x and the perpendicular to the x-axis is ax, so that would be right here. For this purpose, this would be the radius of our circles if we were to rotate it around. Where a is a continuous function, then the volume of S is denoted by v is equal to the limit as n approaches of infinity of sigma from 0 to n of a x star xi star delta x, which, well, we know that's just the definition of an integral, but instead of just the definition of an integral, this is going to be the definition of an integral based on area, so we're going to be calculating about the area. And so, what is it that we're actually trying to do here? Well, all this is saying is we're basically taking this shape and cutting it into little tiny cross sections, an infinite amount of them, if you will, and that would be the area of this circle. The area of this circle, right? And we add up all those areas back to back to back to back, and that'll give us the volume of our shape. So, that is what we're going to be doing for this video. So, for that picture that I previously had on the screen, we were looking at a circle, so circular cross-sections. But how do we find the area of the circle? Well, obviously, we know area is equal to pi r squared. And so, if that were the case, then how do we find what our r is? Well, our radius is going to be defined by the curve, because if we have our curve something like this, and we want to make a solid something like this, well, it changes depending, and when I say it, the radius changes based on where you are in the curve. So here it's maybe that big, and then over here our radius would be almost double the size. And the way we find our radius is, well, from our equation of our curve. So when we do our integration, all we do is we take the equation for our formula, or for the curve that we're using, and then we plug that in for r, and then we integrate based off that. So what if instead of just finding the volume of circular cross-sections for one curve, rather we wanted to find this weird shape where maybe it's a vase that is hollowed out on the inside? How would we do this? Well, we know from our last video that when you're trying to find the area between two curves, you just subtract the higher curve from the lower curve, and that will find the area in the middle. So, with that, we can then see for volumes, it's the exact same thing. So, for this, in order to find the volume of this red curve, the volume between this red curve and this g curve from A to B, all you would have to do is set your radius now to f of x minus g of x, and we would get our volume is equal to the integral from a to b of f of x minus g of x squared pi dx. And that would find the volume between two curves. So now we're going to do an example of how we would actually do this, and it's going to be between two, finding the volume of circular cross-sections between two curves. We're asked to find the volume between f of x equals x cubed and g of x equals x with circular cross-sections. And so I've drawn our little graph, and it states for when x is greater than 0. And we know with the graphs of y equals x cubed and y equals x that our linear function just straight up rise over run 1, and we know that our cubic looks like this. It's going to be under at y equals x at the beginning, and then it will eventually cross paths with it. And we need to find what the bounds are. We know it's going to be 0 for our a, but how do we find b? Well, we know that y equals x and y equals x cubed intersect at 1, right? Because we have 1, 1, boom, they intersect. So we know that our bounds are y equals a, or y equals 0, not y. We have our bounds are a equals 0 and our b equals 1. So we have our bounds, and then what do we have to do? Well, we just have to subtract the two curves and then integrate based off the area formula of a circle, which is pi r squared, where our r is going to be the subtraction of f of x and g of x. So we find that our volume is equal to the integral from 0 to 1 of, well, f of x because, or my apologies, g of x, because our y equals x line is above our x cubed. So then this is going to be g of x minus f of x squared dx, because we're rotating around the x-axis. Well, this is just going to be equal to the integral from 0 to 1 of x minus x cubed squared dx. And then we can just multiply this out, or I guess factor this out very quick, and we say, well, this is just equal to integral 0 to 1 of x squared minus 2x to the 4th minus x to the 6th, and I said minus, but I meant plus, and then we do dx. And then this is very easy. We just do reverse power rule on these integrals, and this is just going to be equal to, well, integral 0 to 1, we have for x squared minus 2x to the 4th plus x to the 6th. That's just going to be equal to x cubed over 3 minus 2/5 x to the 5th plus x to the 7th over 7 from 0 to 1. And when we plug in 0, well, these are all just polynomial terms with no constants, so when we plug in 0 to them, they'll be 0, and we find that our volume is going to be equal to 1/3 minus 2/5 plus 1/7 times pi, because I think I may have forgot that pi in the beginning, and we have multiplied by pi, my apologies, I'll cut that out. And then we continue finding our fractions, and if you were to simplify this out, which you should, we find that this is just equal to 8 over 105 times pi, and that is going to be the volume of this shape if we rotated it with circles. So, that is everything I wanted to cover in today's video. As always, my name was Logan. Thanks for watching. Have a great day.